You're
All right.
live.
Hello, hello.
Hello.
So, hello. Hi, everyone. Today I'll be talking about the serial numbers, as you can probably tell by the fact that I wrote down serial numbers here and also here. Um, so before I start getting into like any of the math or anything like that, I do want to like kind of talk about like what my intentions are here today. Basically, this talk is going to be kind of deep, but also kind of shallow in like two different sort of ways. Like, essentially, what I want to do is like kind of about what the serial numbers actually are. And well, the reason that I emphasize this is because I think there's like a lot of like clickbait explanations out there where like, oh, so serial numbers are made out of two other serial numbers and they form all of the numbers ever. And well, I kind of want to like convey a bit of a more deeper understanding of that. I do want to at least like get into like the mathematics of it, like what formally a serial number is, and like how do you construct the basic ones at the very least. It's also going to be shallow because well, this is not like a seminar. I'm not gonna be like giving out like formal proofs for everything. If I did, then I'd be here all day and probably all night as well. And well, we don't have that much time. So well, I have a bit of formal asterisk here. It's just that I'm gonna be using the word small a lot, and what I mean by small is kind of funny, really. Like the set of all naturals is a small set. The set of all real numbers is a small set. The set of all sets of all sets of all sets of real numbers, that's also a small set. Basically, anything that like you might actually come across that kind of counts as small. Something that would not be a small set would be, for instance, like the collection of full sets or well, the collection of false real numbers, for instance, that's not going to be small. Um, and well, basically, this just avoids like Russell-style paradoxes, where like if we had a set of false real numbers, we could use it to create a new serial number, which would not be in the set, and that would be kind of weird. But yeah, we really don't need to worry about this. I have some keywords if you're like a nerd. And accessible cardinals, growth in deck universes. If you think anything I'm doing is not like fully formal, then that's that. Um, so I think it's better to just get like into the interesting stuff. And well, another thing that I want to preface before this is that there's already like a pretty good series on like combinatorial gaming in the Three Swap channel, given by Mathben, I believe is the username. Pretty cool videos. Those focus more on like the partisan game theory side of this whole thing. I'm going to be focusing more on the algebraic side. So like both of our topics, I'm hoping that they will complement more than they will clash. I don't think that I'm really stepping on his toes here. Uh, but still, I'm going to describe the serial numbers like properly. I'm still gonna have to like explain a bit about combinatorial games, and I'm going to like again. I'm gonna try to focus on the like algebra stuff, but I'm also like, but I am still gonna try to like at least show you how you can play some of these games, even if they're not very boring games. Well, they're kind of boring games. That's what I meant to say. Also, due to my weird setup that I've got going on here, it's kind of difficult to like read chat. So, yeah, if anyone has any questions, feel free to just interrupt me. I won't take it badly.
Yeah, if anybody can't talk, I'll
Um,
just I'll just say it out loud.
all right, awesome. So let's start with like what a combinatorial game is. And well, the thing is, games are like one of these like really broad concepts. Like saying that you're doing something with games is kind of like saying that you're doing something with numbers, right? Like it can mean a lot of different things. Here I'm gonna be focusing on like one very specific, like sort of, let's say, collection of games. Specifically, we have these five different conditions. The first one should make sense. A game is a thing that we're gonna play between two players, and the game alternates turns, right? Like I don't know if you consider something like tic tac toe. Then you have your two players, and one of them places X's, and the other one places O's, and you kind of take turns doing that, right? Like that's what I mean when I say alternates turns. It's one player then the other, and so on. Then both players have perfect information. What do I mean by this? Essentially, I mean that the entire game state is always going to be known by everyone. Like, if you think about other games, like for instance Uno, right? If you're playing Uno against someone else, to like I have my cards and I have like I don't know my numbers here. like part of the game is that the other players are not gonna know what cards they have, right? Like that's kind of the strategy. If everyone knew what my last card was, then they could play around it, and it would kind of make the game not that fun, right? But in the games that we're gonna talk about today, that's not a thing. Like everyone knows everything about like the board, about what moves are possible. There are no elements of chance, nothing like that. So no Uno, no poker, that kind of stuff, that doesn't count. Tic-tac-toe, for instance, would be a game of perfect information because everyone can see the board at all times and everyone can see like what like tiles have already been played, right? So that's something that does have perfect information. No infinite line of play, including non-alternating ones. So this is a bit of a technical one. Essentially what it means is that our game can't last forever. And there's a bit of a subtlety here because we can totally have games that have an infinite amount of potential moves, right? And I don't think there's a very good example to give here, so I'm gonna give a bit of a contrived game, which might make a bit more sense later. Let's say that we have all of the natural numbers in a line, right? 0, 1, 2, 3, 4, 5, so on. And let's like play the following game, right? Like I'm gonna be the first player and I'm gonna say one number. I don't know, 5. And then the other player needs to say a number that's less than that. So for instance, 2. And then I say 1. And then the other player says 0. And then there are no valid moves, so the game just immediately ends, right? So the thing about this game is that like I could have started with any single natural number. I could have started with a million. I could have started with a billion. I can like if me and the other player really want to, we can play this game for like eons, but never for an infinite amount of turns, right? Because if I start with the number n, then now there's only n possible moves that we can make, and n might be a huge number, but it's still just a finite amount. So you might say that this is some kind of well-founded condition. If you don't know what well-founded means, then it's not that important, but basically that's what this should remind you of. You can have huge, enormous, infinite game trees, but there can't be a single line of play that is infinite. And yeah, this is even if a single player could get to move forever, never giving the turn to the other player, then that can't be an infinite line of play either. That's kind of just a technical condition. It's not going to come up that much. So, fourth condition. Whoever's left without a valid move loses, and there are no draws. So this basically just defines what it means for someone to lose or win a game. Like for instance, in this example that I gave of like naming natural numbers, I said, oh yeah, the second player got to 0, and then I didn't have any valid moves, so the game just ended. And in that circumstance, then I would actually lose the game because I don't have any valid moves. The convention here is going to be that whoever has no valid moves loses. And well, I mentioned this because this is not the only way that you can play a game, right? Like you can play games where the player who's left without moves wins. For instance, these are called misère games. I don't know how to say that. It's like French. It's like misère, but with this weird tilde. Yeah, sorry for that. But yeah, the point is that there are other conventions. You can also talk about like combinatorial games with draws. And for instance, tic-tac-toe is a pretty good example of that, right? Like in tic-tac-toe, you can have situations where like where like the next player doesn't have any valid moves, but you don't say that they lose. Rather, you just say, oh, the game is a draw. So I don't mean to say that these aren't like games that can be studied mathematically. Obviously, you can study games like tic-tac-toe or like chess or like checkers or all of these. You can study them mathematically, but they're not in the like class of games that we're going to be talking about today. And oh yeah, there's this fifth condition that's basically just the second condition again. I just wanted to make it. I just wanted to like emphasize that like things like poker, for instance, that doesn't count. And so
maybe I'm missing something here, but I think hex should not be an example, right? Because in hex, the win condition is not the same as the fourth bullet. Because in hex you have to connect the two sides. That's the win condition. It doesn't matter who goes last because, like the player who goes
Yeah,
last is always the parity of the board.
Yeah, that's a good point. I mean, well, I'm not gonna talk about hex here, but like basically the hex is like you have this sort of like parallelogram board, and you have to like put tiles to like connect the path from one side to the other. Yeah, you're right. Like in hex, you do have like sort of different win condition. You can shoehorn it into this definition by just saying, oh, if one player already connected a line, then there are no valid moves after that. Like, but yeah, you're right. It's kind of a different thing. Like you can talk about hex in this sort of like combinatorial game paradigm that I'm describing here, but yeah, maybe it's not the most natural way.
Wait, so if you can just shoehorn things in with conditions like that, then is there actually like a meaningful purpose for the fourth bullet? Because like theoretically, you could do that for any game, couldn't you? Like after any arbitrary condition is met, just say the other player has no moves left. So, like in essence, the fourth bullet doesn't do anything.
I mean, you're kind of right. This is more of a convention. Like this is what I'm gonna define that it loses.
Yep.
Yeah, like for instance, if you have a Miser game, I still don't know how to pronounce that. Like you could just declare that, oh, after there are no valid moves, then you just like add a single dummy move, and then you say, oh, the game ends after that dummy move. Like yeah, you can shoehorn a lot of games into this definition, even those that like don't technically satisfy this condition. But it's easier to just think of this as like a definition. Like we're going to define a game loss when someone is left without moves. And well, yeah, I do list some examples here of like games that we can fit into this paradigm. Which I don't think this collection of games has like a proper name. I guess you can call them like well-founded combinatorial games, in contrast to like loopy games, which can have infinite lines of play and can have draws and that kind of stuff. But well, yeah, here's some examples of that, like Nim. Well, again, this is not a talk about Nim. Let me see if I can erase this. Yeah, I don't really know how to use Create all that well, so I'm just gonna have to undo everything. But yeah, like for instance, Nim. So maybe some of you already kind of know what Nim is. The idea is that you have like these different like piles of rocks, and basically the players kind of alternate turns, like deleting rocks, but it has to be from a single pile. Like, I don't know, the first player can remove these 2 rocks, and then I can remove these 3 rocks, and then the game kind of continues until there are no more rocks left. So that would be an example of a combinatorial game. We're alternating turns, everyone has perfect information because the game state is just like how many rocks there are on each file, and that's all public knowledge. There's no infinite line of play. That's certainly true if we're playing with like a finite amount of rocks. There are also like generalizations to like infinite amounts of rocks, but those also do satisfy that condition. We are playing with the convention that like whoever is left without a valid move loses, and yeah, there's no elements of chance whatsoever. So yeah, again, I'm not gonna like dive too deep into like these examples. I'm mostly just like name dropping. Mostly to emphasize that like the examples that we do have of combinatorial games are kind of contrived. Like maybe you've heard of Nim if you've watched like the other like combinatorial game talks that have been given here, or if you watch, for instance, like one of Numberphil's videos. I think there are a few of those about Nim. You might also know about Chomp. It's a similar concept where you basically like take things until you can't take anymore. Here's a bit of an illustration. Basically, the idea is you kind of chomp out you basically just like eat the chocolate. Like you can take these 2, or you can take like these 3, that kind of stuff, until you get to like, and basically the rule is that you can't eat this last piece of chocolate because it's poisoned or whatever. And well, yeah, that also satisfies all of our conditions. And yeah, there's other games like Hex, again, if you kind of shoehorn it in that way that we described earlier. Toes and Frogs, that's another like example that gets listed sometimes, but the point is that no one actually plays this game, so let's be completely honest. Like I'm using here non-examples, and it's like tic-tac-toe because that has draws, chess because again you can like shoehorn it, you can like analyze some end games of chess using CGT, but since it has draws, it doesn't really fit into the definition that I'm giving here. Solitaire because that doesn't, you don't have perfect information, you don't know what all of the cards are. I don't know, Balatro, basically anything in practice. It's not going to be a combinatorial game, which is a bit unfortunate, but you know, there's still fun things that we can do with this somewhat limited definition, right? So, well, any questions so far? Let me just check chat real quick. Yeah, like Infinite Chess and Checkmate and Omega, those are examples of like games that have an infinite amount of states, but which don't have any like infinite lines of play. Can anti-chess be a misery game? I mean, the thing is, you can. Well, I don't know what you mean by anti-chess, but you can totally play chess to lose, and that would be a misery game, for instance. Do we assume both players are perfect logicians? That's a pretty good point. So basically, the idea is that like when we analyze a game, when we talk about who wins or who loses a game, then yeah, we're basically going to be assuming like the best case scenario for like both players, right? Like if we say that a given game is won by the by the first player, let's say, then what that really means is that the first player has like some kind of strategy that guarantees them the win. So I'm not saying that they will always win no matter what, right? But I'm saying that they can win if they play smart, basically. So yeah, in that way we kind of do assume that both players know what they're doing. Any other questions? I see someone typing. Yeah, basically, like you can always like take a game and say, oh, so whoever won now loses, whoever lost now won. That's kind of what playing a misery game means, really. It's just like now you're playing to lose. I mean, misery basically means miserable, I think. Again, I don't speak French. I'm really sorry, but yeah, basically that's the idea. So, all right, I'm gonna continue. All right, so let's get into the mathematics of this. So, how do we like represent the game? We can obviously like draw diagrams like this, right? But we can get a bit more abstract as well. And the way that we're going to do this is, well, let me just read this out. So mathematically, a game is some kind of pair, right? Like, yeah, a game is a pair. And S is going to be like the set of possible game states which the first player can reach. And since we're writing it on the left, we are just gonna call player 1 left, right? And T is going to be like the possible game states that player 2 can reach. And well, it's on the right, so player 2 we can call him right. And to give an example of how this works in practice, like we could take tic-tac-toe again, right? Which again isn't like a combinatorial game in like the strict definition, but we can still sort of use it to get the idea. So, what would tic-tac-toe look like as a pair? So, the set of possible moves for the left player, well, the left player, let's say that they are X, and let's say that the right player is O. So, the set of possible like game states, or simply games, that the left player can reach would be like placing here on the top left, placing here on the top middle, and all the other 9 different options, right? Well, it's 9 in total, I should say. And yeah, this is gonna be like the set for like the left player. And for the right player, well, it's going to be another 9 positions, right? Like they can play O on all of the 9 different squares, right? Yeah, sort of like this. So the game of tic-tac-toe would essentially look like this, like in the mathematical sense of a game. It's a pair, and here are the moves for the left player, and here are the moves for the right player. And well, the way that we generally write down these pairs is, instead of writing it as like pair with like commas, S, comma, T, we're going to write it down as like S bar T. This is how we're gonna like write down an arbitrary game, right? And basically this just means S is like the set of positions that the left player can immediately reach, and T is the set of positions that the right player can immediately reach. And well, the basic idea is that games are basically, I mean, I gave here as one example of a game. Now we can talk about like, what does the set of all possible games look like? And well, that's simply, well, this is a bit hard to describe, honestly. It's a bit of a doozy, because there are not a lot of like structures in mathematics that are defined in this way, at least not usually defined in this way. But the basic idea is that a game is like, well, the structure of all games is kind of like the smallest structure that is closed under this pairing operation. And well, this is kind of where like the whole asterisk with like small sets and such comes in, because obviously, like, if we could describe the set of all games, then we could define like a game where like the left and right sets are like the set of all games, and that leads into like weird paradoxes, right? Like Russell's paradox, that kind of stuff. So basically, we have to like constrain the left and right sets to be like small. And again, you really shouldn't worry about like what the word small means. It basically just means not the size of literally the entire universe. And if we want to be even more formal, we can describe games as a sort of an inductive structure. Like, for instance, let me see, does this work as an eraser? Close enough. There we go. So to give an example of what I mean by this, I think this is something that I should probably like take a bit more care to explain well. So instead of talking about games, let's talk about natural numbers for a bit. So yeah, I know, right? Clickbait. We're talking about natural numbers now. That's, how do I get rid of this? Escape something.
I don't know about the program
Wow.
you're using, but on GIMP, what you would do is like open the rectangle select tool and just click it anywhere on the screen without dragging anywhere.
Oh,
Yeah, there you go.
there we go. Thanks. Yeah, so we're going to talk about natural numbers now. I know, clickbait. But the idea with natural numbers is that we can describe them via sort of like inductive process, right? Like, what is a natural number? Basically, we can say that there are two types of natural numbers, right? There's 0, which I am counting as a natural number for the purposes of this talk. But there's also like a successor operation, right? Like, if we already have a natural number n, we can define the successor of n, which is just going to be like n plus 1. And in a formal sense, we can say that natural numbers are like the smallest structure that's closed under these two operations, right? Like, if you only have the number 0 and you have successors for every natural number, then that gives you all the natural numbers, actually. You get 0, and then a successor of 0 is 1, then a successor of 1 is 2, then a successor of 2 is 3, and so on. And the reason that I bring this up is because games are kind of, we can describe it via the same sort of inductive process. Instead of having like a successor operation, we're going to have like this sort of pairing operation. So we can say that a game has this operation, like the S paired with T operation, and if S and T are like small sets of games, then this pair is also going to be another game. And basically, games are just the smallest structure that's closed under this operation. I hope that sort of makes sense. And so to like give examples of games, well, we're gonna do that in just a bit. But like for example, we can take S&T to be the empty set, since we haven't rolled any games yet. That's kind of all we could do. And we get this game, which we're gonna call 0. Again, I'm gonna go into a bit more detail on this in a bit. Then what you can do? You can make games like, I don't know, put 0 on one side and the empty set on the other. And then you can put like 0 on both sides. And then you can like put these games in the sets of other games, and you can just kind of keep going, right? So that's kind of the idea. Games are like this structure, and you can like pair them up. And basically, every game is going to be constructed via this sort of process. I hope that this makes sense. It's kind of a bit difficult to explain. Like, the key word here really is inductive type, but, well, I mean, unless you've like worked with Haskell, it's probably not something that most people are very familiar with. So, yeah, I should probably ask if like
maybe you were trying to dodge this question, but I'm too curious to not bring it up. You've now, it sounds to me like you're now bringing up two separate definitions. One being sort of the like inductive structure that you gain from nesting these things within each other, and the other being the condition about not having small or having the left and right sides be small. Are you claiming that those two definitions are the same thing, or
Oh, like no, it's the same thing. Like here I'm also requiring that S and T are small. Like
okay.
That's kind of necessary, or otherwise you could run into like all sorts of paradoxes.
Is there a way that they could not be small when constructed inductively?
Well, the thing about the inductive definition is that being small is also like part of that definition. I just forgot to mention it.
As in, it's part of it in the sense that it's a requirement that is added on top of it being constructed inductively, or like...
Yeah. Like, basically a game is like, it's made out of two small sets of games. That's like the inductive construction.
Oh, a small set
I can relate. What definition of small are you using?
Category theory. Basically set sized.
Okay.
As opposed to class sized. Again, I'm trying to not like go too deep into these details because they're not interesting. But
yeah, I think I follow you now. We're not talking about
what I would say is like, if you don't know about category theory or set theory, you can ignore the word small. I think it'd be a different way to say it.
Yeah, but the thing is that like if you really take this literally and you try to like put like for instance, like what happens if we try to make a game where like the left and right sets are like the entire collection of games? Well, then the left player
you
can
haven't
move
justified
to...
that that's a set. Like, that's not a like that's a problem. That's a set theory problem. That's not a serial number or game theory problem.
It is a game theory problem. Like, let's call this game G. So then the left player can move to any single game whatsoever, and that would include G.
I think what Jared is saying is like
to any single game, and they go to G, and it just kind of starts looping around, and that's not well founded.
But
I guess what I was trying to say is like the fact that there's a problem with your example G is a theorem of like your particular set theory and how you've set up the sets or whatever, and it's something like we shouldn't be worrying about for your talk today, I assume.
Yeah, sorry for derailing. I was too curious.
I mean, yeah, I guess. Like,
the word small doesn't appear in like a textbook on combinatorial game theory proof.
I mean, well, the reason I bring this up is because, like, for instance, like, Conway really tries to, like, really makes a point about how, like, these sorts of games are, like, connected to, like, sets within CFC. And I mean, the reason that he makes that connection is, like, basically to avoid things like this from happening. Because if you just say that S and T are, like, sets in CFC, then the smallness condition kind of gets in for free. But, like, really what you just need is, like, a size condition. Like, as long as the games don't get too large, you won't run into issues like this. So, yeah, again, this is just, like, asterisk. So this is not something that I really want to, like, spend too much time thinking about. because sets versus classes solve that is mostly uninteresting. So I think we should probably just move on.
Yeah, that answered my question.
Well, yeah, but the question is, I guess I did have the question of like if everyone was on board on this like inductive process thing that I was defining. Does the game go from S to T to either one element of S or one element of T, depending on who plays? Yeah, exactly. Like, S are like the options for the left player, or player 1, or whatever you want to call them. And T are the options for like player 2 or right. And, in some games, S and T are always going to be identical. In some games, they might be completely different sets, that kind of stuff. So, alright, let me delete this. There we go. So yeah, I think it's better if we just go over some examples, right? And I say here sarcastically, these are some simple examples which you can play with your friends, and I say that sarcastically because none of these games are very fun, but we can still study them, right? So the very simplest game that we can define, I already defined it. It's just the game where no one has an option to do anything. This is it. And we call this the zero game, and the fact that I'm using the number 0 suggests that there's some kind of extra structure, and there indeed is, and I will get to it. But for now, we can take this as definition, right? Like the game 0 is defined to be this game. And, well, anyone want to play with me?
I don't.
Yeah, so this is not a very fun game, and like I don't know, say you want to play with your friend, and then you say, "All right, you can start.
I'll play
the first move."
Yeah, I'll play with you if I go first, or rather, if I'm the starting position, you move first.
Yeah, exactly. Like whoever moves first instantly loses, and that's it. That's the entire game. You just there's not a lot you can do with the 0 game, but it is the simplest game in a very formal sense. In fact, in a very precise sense, it is the simplest game. So it is an important game, even if it's like not fun at all. So what else can we do? Using the 0 game, well, we can start to define other games which make use of the 0 game. So for instance, we can have 1, which is going to be defined as this game. The left player can move to 0, and the right player has no moves at all. And here's where I do kind of have to emphasize that, like, left and right, they're kind of like saying black and... Well, no, it's not exactly like that. Like, what I'm trying to say is that, like, left and right is not the same thing as saying first player and second player. Like, you can have a game where, like, right starts as the first player, or you can have a game where right starts as the second player. You can sort of think of it as, like, black and white pieces, except that, like, you're not requiring that what else always starts. So that's why the analogy just doesn't really work. I don't know if there's, like, a lot of games where, like, you have different, like, where you have, like, these two different players and it doesn't matter which one starts. I can't think of any example right now, but yeah, the idea is that, like, first and second player is not the same as left and right. That's basically all I'm trying to say. And, well, we could think what happens if we try to play 1.
Okay, this one I want to play with you. So
all right.
I'll assuming I'm left. And we're alternating.
Yeah, you can be left.
Okay, sweet. I'll take my 0 game.
Okay, so we move to 0, and now it's my turn, and now I lose. Awesome, you won.
Yay.
So that's pretty nice. And so basically, if left starts the game, they have a winning strategy. And what happens if right, try to start the game? So if I try to start the game, I have no moves at all, and I immediately lose, so you won again. So basically what happens with the 1 game is that left always wins. And, well, 1 is kind of simple enough that, like, in this case, it's basically guaranteed. Like, there is literally no way for left to lose. But again, we are kind of assuming that the players all are, like, super intelligent or whatever. So really what matters is that left has a winning strategy. That's kind of the important thing. And that's independent of whether they start or whether they go second. And, well, we can contrast that with, like, the case of 0, where it's like the second player wins. In fact, I think it's better to, like, make a sort of table here. Basically... So, yeah, we have, like, left and right. Where... How do I tabulate this? Let's put it like this. Left goes first or second. That's gonna be our tabulation, basically. So in the case of 0, what happens? If left goes first, they lose. And if left goes second, they win. In the case of 1, if left goes first, they win. And if left goes second, they also win. So basically, 0, 1 covered 2 or 4 different cases, right? And what we're gonna do is we're gonna like find 2 other games that like cover the other cases. So the very next game that I want to talk about is just the negative of 1. And again, I'm using symbols like 0, 1, negative. It suggests that there's an algebraic structure, and there is, but like for now, again, it's better to just treat this as definitions. And the game -1 is basically just the game 1 but flipped. The left player has no possible moves, and the right player has a single move to 0. So what happens here? Well, it's kind of the opposite of what happened for 1. It makes sense, right? If left starts first, then they have no valid move, so they immediately lose. And if left goes second, then what happens is that right plays, moves to 0, and yeah, then the left just loses. So those are 3 of the 4 possible different outcomes. And now for the last one, which is kind of a weird outcome, we have to define this game, star. And star is going to be the game where both the left player and the right player have a move to 0. So what happens here? I don't know, anyone want to play this one with me?
I guess I will. Do I go first or second?
Alright, let's say you can be a left again.
Okay, sure. And do I go first?
Yeah, so
right,
you have a lot of options. You
0.
can move to 0.
Yeah, take 0.
Oh, wow, I lost again. Wow, incredible. So, left going first wins. That's pretty nice. But what happens if I go first? Well, now I'm gonna move to, well, 0.
Oh no, I lost.
You lose. So, yeah, you can kind of see how this table fills up, right? Like, basically, you have like these 4 different possible outcomes. Like, left can win or lose going first, they can win or lose going second, and yeah, basically all 4 outcomes are possible. And the simplest games that like represent those outcomes in a way are these 4, right? 0, 1, -1, and star. And well, I mean, star is kind of weird because like the other ones are very clearly named like numbers, and star is just named like star. So what's going on there? Well, we'll see that in a bit. But yeah. So let me just see if there's anything in chat. Are the elements of T dependent on the elements of S like in a regular game? Not really. Like S and T can just be whatever. Like, you can have a game where S has a billion gazillion possibilities and T has nothing at all. You can do a lot of weird stuff like that. Flipping L and R as negation. You're getting a bit ahead of myself. It's not exactly that, but it's pretty close. The equation x equals minus x has two solutions. Yeah, it has a lot more. That's something that I'm not really going to talk about here, but the keyword is impartial game. Any other questions? I see someone typing, so I'm just going to wait a bit. Yeah, S and T basically represents like what possible moves you can make. Like, it might make a bit more sense to think about like S and T are like the possible game states that you can reach in a single move. The thing about games is that like game state and game are the exact same thing because we have perfect information. But maybe game states makes a bit more sense to. At least it makes a bit more sense to me. I think I'm gonna continue. So, well, these are like the four like canonical examples of games. I have the word serial numbers here. These are not serial numbers yet. We'll get to that in time, but it might be a good idea to like go over a few more examples of games. So another example I wanted to talk about are the natural numbers. Yeah, you can encode natural numbers as games. We already saw one, but we can really do any natural number. And the way this encoding works is that n is going to be the set of, well, from 0, 1, 2, all the way to n minus 1. Those are the moves for left, and right has absolutely nothing to work with. So, it's easy to see that n is like the same type of game as 1 is, in the sense that like, well, I mean, for n other than 0, then left always wins. But it's not only that they win, it's that they actually have like a lot of leeway. Like, for instance, if you imagine the game where like, I mean, I don't know, we can imagine the game 100, right? The game 100. So, if we played the game 100, and maybe we say, we really want the left to exhaust all of their options, they're gonna have to like move over and over and over. Well, they can do that 100 times, you know? They can just keep going 99, 98, 97, 96. And right is never going to have anything to do. Like, in a sort of informal way, you can say that the number n represents an n move advantage, right? Like, it basically means left has n many free turns. And, well, yeah, again, you can see that if n equals 0, then this is just this game again. If n equals 1, then this is just this game again. So those are like kind of special cases of this construction. And, well, we can in fact go a bit further. This is not going to be a talk about the ordinal numbers. I'm probably going to do that some other day. But, you know, just to give a quick example, we can consider... Let me just erase some things here. We can consider this sort of game, Omega, where the left has 0, 1, 2, every single natural number. All of them are options for left, and right has absolutely nothing to work with. So, in some sort of way, it's like an infinite move advantage for left. And, well, it's not like literally an infinite amount of moves, because, again, after left makes their first move, they will have to land on some natural number. It can be immensely large, but it's still going to be a finite amount. So basically, Omega means that left can keep playing turns for as long as they want, but not for like infinitely many turns. And you can kind of see how this generalizes to other ordinals. Again, if you know about the ordinal numbers, then yeah, that's kind of how you encode them as games. If you don't know about real numbers, then that's okay. That's not the topic of the talk today. You can kind of stick with omega as like your example of what's going on. So yeah, they get to pick how many moves they want to make. Successor of n equals n bar empty set. Well, okay, I mean, yes and no. I mean, yes, in the sense that, like, well, for instance, like if I have the game 2, you can write this, well, the definition that I'm giving here for the number 2 looks like 0, 1, bar nothing. You can also define it as like 1 bar nothing. These are equal in some sense that I'll make more precise a bit later. But I do prefer this construction because this one generalizes to the ordinals and this one doesn't. What else? Yeah, like, basically, it is a reasonable definition, but it's a different definition and it doesn't correspond with what... we'll get to, like, game equality later. That's a bit of a thorny topic, but we'll get there when we'll get there. So, let me undo all of this. One last example, just so like we get a bit of an idea of like what kinds of games there are out there. 1/2. What's 1/2? Like, I just told you that, for instance, the game 5 corresponds to like a 5 move advantage for left. What's 1/2? It's a half move advantage. You can't say it's only 1/2, you know? Insert that one joke from the Mario 64 video here. But, well, maybe it makes more sense if I just write it down. 1/2 we define as this game. Left has 0 as its only potential move, and right has 1 as its only potential move. So what happens if we play this one, huh? Anyone want to play with me?
I'll play with you.
I want to be left, but you can go first.
No, go ahead.
Okay, so you're gonna be left, but I'm gonna go first, so I'm gonna be right. And, well, I'm gonna make my move to, well, my only possible move to 1. Your turn.
Okay, I'll make my only possible move to 0.
Yeah, so 1 is defined like this, so your only move is 0, and oh wow, I lost. Drats. So, alright. Basically, if the left goes second, let's make our table again. First and second for left. I went second and I lost. So... No, wait, what? No, sorry, you were left. I'm sorry. Yeah, sorry. I'm right, you're left. You won as the... Oh, yeah, you won as the first player. Sorry, I'm like getting mixed up.
No, I won as the second player.
No, you went first, didn't you?
No, right went first, won. Therefore, left went second.
Oh, of course, yeah. Sorry, the thing is that, like, we keep swapping between, like, if I'm left or you're left, and it's kind of confusing. But, I mean, we can see that if left had gone first, which is you could have moved to 0. Let me delete this. Oh, wow, there has to be an easier way to do this, and there probably is, but I just don't know how to use the software. If you had gone first as left, then you could move it to 0. And well, then I lose again, right? Because 0 is kind of like the losing game. So, yeah, this is like in the same outcome class as 1. Like, left wins in both cases. So why do I call this 1/2? Well, I can't quite explain yet because I haven't like got into like game arithmetic, but I can kind of spoil it, right? The idea is that there's going to be like some sort of way to add numbers together, and we're going to get the equation that 1/2 plus 1/2 is not quite equal, but kind of equal to 1. Again, foreign topic, I'll get there. But that's kind of the idea of why this is called 1/2. And we can, in fact, like make other fractions. Again, I'm not going to go into the details just yet, but the idea is that they satisfy similar equations where, like, if you add them to themselves, you get, like, the other fractions. So, for instance, 1/4 is going to be this game, where left can move to 0 and right can move to 1/2. Or, I don't know, 3/8, that's going to be the game where you have 1/2 for left and... No, sorry, 1/4 for left and 1/2 for right. And you can kind of keep making fractions like this. It's... Again, I'm not going to go into the details here, but you can kind of see what's happening. Where, like, for instance, 3/8 is, like, exactly in between of 1/4 and 1/2. Or I can make, like, I don't know, what else? 7/16, which could be 3/8 and 1/2. And that's also precisely in between. So you can make a lot of fractions like this. All of these fractions are going to have, like, denominators that are powers of 2. That's kind of important. Yeah, this probably doesn't make all that much sense if we haven't really seen how to add up games yet. So I think that's what we should do next. So, well, let me just check it, chat real quick. Yeah, exactly. Half an A press. Is one... Not exactly. Yeah, no, that's not quite right. 1/2... Let me write this down. 1/2 for left and 1/4 for right. It's not going to be a number. And again, I'm getting quite a bit ahead of myself, but this is basically just going to be like some other type of game. It's not a fraction in the same sense that these other ones are. And basically the idea is that, like, since 1/2 is greater than 1/4, then, like, weird things happen. Well, I mean, this is a valid game. It's just not, like, one of these kinds of games. The keyword is numeric, and again, I'm kind of gonna get to that. Like, for a moment, it's probably better to just treat this as a definition, and we'll explain why it's a half when we get to that. And so, yeah, let me... How do you add game?
FYI, your audio is cutting out for me.
Because so far, all of that I've done is, like, really suggestive, so yeah, I won't keep... The very first thing that we're going to do is we're going to define an order relation in games. And this is another one of those definitions where, like, it only makes sense if you have details that I want to give, like, further down in the talk. So you're gonna have to trust me a bit on this one. I promise that it will make more sense in, like, 10 minutes. But the idea is that we define what game comparison is inductively. We can use induction because for pretty much the same reason we can induct on the natural numbers. And this is one of those formal details that I won't really get into. But, well, yeah, the idea is that, like, you can do induction in games. Where, like, you can basically define a game if you already assume... Like, if you can define, like, a property of games, or you can prove a property of games, assuming that you've already defined it for all, like, left and right options of the game. And so that's kind of what we're going to do here. We're going to say that G is less or equal than H whenever, and this is going to be kind of weird, when H is not less or equal to K, for every k in the left set of G. You know what? I'm gonna abuse because most authors just kind of do this. But instead of writing like an element of like the left set of G, I'm just gonna write like this to like to refer to like an arbitrary element of like the left set of G. So basically, this has to hold for all left elements, not just one. And also, there's two parts to this definition. We also need that everything in the right set of H is not less or equal to G. So that's what G is less or equal to H is defined as. And, well, yeah, this probably doesn't make any sense whatsoever right now. But I think it makes more sense if we try to plug in 0. And, well, actually, I'm not going to get ahead of myself. I think it's better to first like talk about like what properties this order has, and then we'll talk about why it makes sense. So, yeah, what properties does this have? Is reflexive. And what reflexive means is just G is less or equal to G. Which, I mean, kind of makes sense considering that I'm like, I mean, it's not less, it's less or equal, right? So this kind of makes sense. This is also transitive. This is a pretty tedious proof to do inductively, and again, I'm not going to be doing any proofs here, so you'll have to like kind of take my word for it. But what transitive means is that if G is less than H, and also H is less or equal to, I don't know, K, then G is going to be less or equal to K. So that's nice, reflexive, transitive. Do we have anything else? No, not really. And this is why I said that equality was kind of a thorny concept. Because in the literal sense, this isn't really, we don't really have antisymmetry. And, well, what antisymmetry means is that, I'm running out of space here. I'll write it down here. Antisymmetry. Kind of fancy word. Such a shame that we don't in fact have this. What that means is that if G is less or equal to H, and H is less or equal to G, then G is equal to H. And in a literal sense, this isn't really true. And in fact, we already saw an example earlier when someone asked like about the definition of the number 2. Like, I said that you could define it as like this game. They were asking if you could define it as this game. And the thing is, these are sort of the same game, but not really. And the sort of same here means that if you have this first game, I don't know, G, you have this other game, H, then you do in fact have that G is less or equal to H, and you also have that H is less or equal to G. Like, if you run over this like weird inductive definition and you kind of like do the entire calculation, then yeah, you can prove that these are in fact like less or equal to each other. And now the thing is that a lot of authors do just go ahead and say, oh yeah, these are equal games. I don't really like doing that because, well, you can kind of see that they're not in fact equal. Like, for instance, with G, then G, the left player has the option to move to 0, right? In H, the left player does not have that option. So in like the literal sense, they're not made out of the same sets, so they're not equal games, even though they are like the same in like this order sense. And what I'm gonna do is I'm gonna call them order equivalent. And what order equivalent means is that G is less or equal to H, and H is less or equal to G. And I like to write it using this sort of like approximation sign. I don't think this is a thing in the literature, but it's kind of just a thing that I like to do, so I'm gonna do it. This is my talk. And well, yeah, anti-symmetry basically boils down to the fact you can have G order equivalent to H, but not like literally equivalent to H. And well, I should probably also mention that in the literature, the way that authors generally call games that are like literally equal, they say that they are identical games. And they write them down using this sort of like triple bar. Again, I don't like doing this because I don't really like trying to redefine what equality means. So yeah, I'm not gonna like follow this convention, but I mean, you can do it if you want. That's your thing, right? So did any of this make sense at all? 100% with me. Okay, alright. Yeah, that's another one of those topics that I was like kind of worried to explain because like a lot of the authors don't really like talk about these sort of details, but I think they're important. Maybe it's just like the formalization part of me speaking, but you know. Alright, everyone with me. That's good. So let me now try to explain where this like very weird less or equal relation comes from. The idea informally is that wait, let me delete all of this. There's gonna be someone screaming at me in the comments, no, you were supposed to use this keybind. You should just have made the background color black. And they're probably right, but I don't know how to do these things. I downloaded this software literally yesterday. So, yeah, let me try to explain like what this definition actually means. So, intuitively, G less or equal to H just means H. It basically just means left prefers H to G. No, actually, you know what? I think this doesn't make sense if I haven't talked about addition. So I'm still not going to explain what this means. But yeah, I think it makes more sense if we just try to plug in 0 and we see what happens. So let's do that. What does it mean for a game to be less or equal to 0? Or what does it mean to be greater than 0? And well, I should explain here what what greater even means, right? So G less than H, we're going to define this as, I mean, we'll generally define less than as meaning less or equal but not equal, right? But since we don't have anti-symmetry, that's kind of weird to do. So instead we're going to define this as G is less or equal to H and not H is less or equal to G. This was the less than symbol is going to mean, right? I should also explain this other weird symbol that I have here in my document. This is the fuzzy with or confused with symbol. And what this means is that neither G is less or equal to H or H is less or equal to G. So you don't have any of them. So, all right. With
Just
that
an
out of the
FYI,
way,
there was a question in the chat. Is there a notion of who has more options when comparing equivalent games?
I don't know. I don't think so. I mean, generally, like if you're studying like games from a game theory perspective, then equivalent games are basically the idea is that equivalent games are in some sort of way like the same thing from a perspective of who wins and who loses. It's more precise than that, and it has to do with addition. And yeah, I really should have just defined addition before I defined the ordering. I'm starting to realize that. But we'll get to there pretty soon, so I'm hoping that it will all kind of click after that happens. And, well, with these symbols defined, like the less than symbol and the fuzzy with symbol or confused with symbol, it's kind of easy to see that there's only like 4 different ways that like 2 games can compare with each other, right? And it basically boils down to like the different combinations of... Wait, let me move this a bit to the... No. Let me move this a bit to the... Can I move it? Can you let me move this? It's not gonna let me move it, so I guess I can't. I'm gonna have to delete this. So basically there's 4 different ways that like 2 games can compare to each other. And it depends on like whether you have G less or equal to H, or H less or equal to... You know what, I'm just gonna like delete this as well. I mean, again, we'll get into like why this definition makes sense in just a bit. So there's like 4 different ways that 2 games can compare to each other. And it depends on whether you have G less or equal to H, or H less or equal to G. And basically all 4 possible combinations are possible, in fact. So what are these combinations? Let me actually write this a bit here to the left. So if you do have G less or equal to H, and you also have H less or equal to G, then, well, that's just like the order equivalent relation that I defined earlier, right? Like, that's no problem. We already kind of know what that is. If G is less or equal to H, and H is not less or equal to G, well, that's what we defined as G being less than H, right? If G is not less or equal to H, and H is, in fact, less or equal to G, then that's what H is less than G means. And finally, if we have neither of these, then yeah, that's like the other new symbol that I introduced, like the confused with symbol. G and H are incomparable, basically. You can't order them in either way. And so the reason that I bring this up is because, well, we have 4 options here. Earlier I was talking about like different outcomes of games, right? Like I mentioned that if you had like, for instance, the 0 game, the 1 and -1, the star, that these also give you like 4 different outcomes, right? For like depending on if left 1 as the first or the second player. And well, the idea is that these kind of correspond to those same 4 outcomes, especially in the particular case where H equals 0. So let me just delete these things. Oh. So if we compare things to 0, something really nice happens. The idea is that a game is going to be order equivalent to 0 whenever... damn it, I don't have like enough space here, but well, you can kind of read the document, I think. So these 4 outcomes correspond to like the different outcomes for left winning or losing as the second or first player. If 0 is less than G, then you can prove that left has a winning strategy as both players. So this is kind of like the win-win outcome. I don't have a lot of space to write it down here, but I mean, I think it makes sense. If 0 is less than G... Oh, no, wait, sorry. The other way around. If G is less than 0, then left always loses. If G is greater than 0, then left always wins. If G is order equivalent to 0, then left wins only as the second player. So we can write down that as lose for the first player, win for the second player. And if G is incomparable to 0, then left wins only as the first player, which we can write down as like a win for the first player, a loss for the second player. And, well, I'm not going to go over the proofs, but these are kind of definitional. Like, basically, if you like expand out this definition and substitute 0, it kind of gets simplified because 0 doesn't have any left or right moves. And so you can kind of build a winning strategy from that. But yeah, I think this is already getting pretty long, so I probably shouldn't go through all of the details. What we can instead do is like we can try to verify that like the games that we had built earlier do kind of fit into this framework. And, you know, as an example, like the game 0. Well, 0 is obviously order equivalent to 0. And as we saw earlier, then, well, 0 is lost by the first player and it's won by the second one, so this seems to check out. The games 1, 2, 1/2, all of them, had this property that the left would always win them. And, well, the fact that they're written as positive numbers should kind of explain why that is. And yeah, you can in fact prove that 0 is less than all of these numbers, for instance. With star, well, star is actually going to be in this outcome box here, down here, right? Like, you can prove that neither star is less or equal to 0, and also 0 is not less or equal to star. And so it lands in this outcome box, and, well, as we saw, star was in fact won by left as the first player, but they lost to the second one. So, at least this framework sort of suggests that like this sort of comparison makes some sort of sense. Yeah. I hope I haven't lost anyone just yet. Something like that effect about outcome comparison to 0 was also proved. Oh, awesome. So, well, yeah, you can go check that talk out if you want. I was kind of hoping that we wouldn't spend so much time talking about combinatorial games because I haven't even gotten to like the surreals. But I should probably finish out at least like this part about arithmetic. So let's quickly like define what it means to like negate and sum two different numbers. So negation, actually one of the commenters already like pointed it out. Negation is kind of just swapping the two players, but in a more precise way than just swapping the left and right sets. And I can write down as an equation. The negative of G is the negative of the right set of G for the left set, and the negative of the left set for the right set. And, well, I think it makes a bit more sense if I like write down some examples. So for instance, we had already seen that like 1 is this game. 0 for the left set, empty set for the right set. So the negative of 1, what's that going to be? Well, the first thing we do is we swap the left and right set. But we also have to like negate everything on both sets. So it's going to be like the negative of the empty set, and then the negative of 0. Except that, well, if we are negating an empty set, we're not actually negating anything, so it's just the empty set again. And the negative of 0, I mean, I probably should have started with that one, but like, I think it's pretty easy to see that the negative of 0 is just going to be 0. So, yeah, the negative of -1 works out as the thing that we said that it was, which is the empty set for the left player and 0 for the right player. I think a more interesting example might be what happens with 2. So for instance, I define 2 as 0, 1, bar, nothing. So the negative of 2 is going to be the negative of the empty set on the left side, then the negative of 0 and the negative of 1 on the right side. And well, again, the negative of the empty set, that's just like the empty set. The negative of 0 is just 0. But we can see that we have a negative of 1 instead of just the 1. So it's not literally just swapping the left and the right sets. And well, the idea behind this is that like we're not just swapping the players for the very first turn, we're also swapping the players for every turn that goes after that. So that's kind of why we have to like recursively negate things. But yeah, it is basically just swapping the left and the right players. So, I don't know, for instance, if we want to play the negative of chess, then that basically just means that instead of me being, I don't know, white and you being black, then now I'm black and you're white, right? So, it's kind of just that. It's not very difficult to really... I mean, it should make sense, I think. I think this should make sense. Does it make sense? Yeah, -0 is the same as 0. And yeah, like, -0 is what the authors might call identical to 0. Like, they are exactly the same game, not just order equivalent. Yeah, it's recursive swapping. Exactly, you put it better than I did. So, yeah, that's exactly correct. So, yeah, negation. Negation is kind of really easy. Now, what's going on with addition? Addition is another construction that, like, maybe looks a bit intimidating if you, like, write it down in symbols, but it makes sense if you, like, actually try to play the games. So, what addition is basically just playing two games side by side. One second, where's the paint bucket? There it is. Adding up two games is basically just playing them side by side. And the rule here is that you can play in one of the games, but not in both at the same time. So again, I think it makes more sense with an example, like say that we have a game here of chess, which I'm not going to draw out because that would take way too long. And we have a game here of checkers. And again, these aren't like games in the like strict sense that we're talking about, but we can use them for examples, at the very least. So what would the game of chess plus checkers look like? Well, I don't know, let's say that I am the left player, which we'll say is like white for chess and I don't know, maybe red for checkers. I don't actually know how checkers works. But basically, what would be my possible moves? I could like do a move here in chess, or I could do a move here in checkers. I can't do both at the same time. I kind of have to choose one or the other. And so that's basically what adding two games means. It just means you play them side by side and each turn you make a move in one or you make a move in the other. And formally, if we try to like write it down like as an equation, we get this thing. And well, the idea is that GL plus H, this basically just means that the left player made a move in G. G plus HL means that left made a move in H. GR plus H means that right made a move in G, and G plus HR means that R made a move in H. So those are like the options, right? Like each player can make a move for their own player in one of the games, but not in both. Does this make sense? Yeah, exactly. If you play Go, then well, it's not just Go. Like, okay, actually, I don't want to talk about this in a bit more depth. The idea behind addition is exactly the idea of like, I mean, you're usually not gonna play like chess plus checkers, but you might have some sort of other game. Well, Go is like the most common example, where like as you play and you do moves, the board sort of naturally splits up into like independent parts, right? Like, I'm not gonna make a whole diagram of a Go game because I can't do that. But you might have some sort of like endgame situation where like the board kind of split up into like these 4 different sections and none of them are gonna ever interact with all of the others. They're kind of closed off. And then you can basically like examine this big position as a sum of 4 different subpositions. And then if you can like figure out what's going on in each of them, then you can just kind of add them up That's kind of the motivation for addition. And in fact, you can pretty much argue that like the theory of games that I'm describing is like the theory. It's like the theory of like subpositions of larger games. That's basically what CGT excels at. If you have like some sort of game that like splits off into like these different components, then CGT is going to be like pretty cool with that kind of thing. But yeah, here I did want to emphasize a bit more like the algebra of games rather than like actually trying to play them. So let's take a look into that. Like, what does the algebra of games actually look like? What kind of identities do we have? Do we have commutativity? G plus H equals H plus G? Yeah, we do. We can prove that through induction, which again I'm not going to do here, but you can do that. Do you have associativity, which would be G plus H plus K with the parentheses in one way equals G plus H plus K with the parentheses in the other way? Yeah, you do. And I mean, again, this kind of makes sense, right? Like, if you add two games together, it doesn't matter if you put them side by side or like the other way around. If you play 3 games, then that's kind of just playing 3 games. It doesn't matter if you play 2 and then one of them, or 1 and then 2 of them. It's kind of the same thing. What else do we have? G plus 0 equals G. Yeah, we totally do have that. That works perfectly fine. And well, since we have commutativity, then we're also going to have 0 plus G equals G. So everything seems to work fine so far. So what happens with subtraction? And, well, I mean, I haven't defined subtraction, but you can probably guess that subtraction is just going to be... Well, let me write it down. So, subtraction, G minus H, this is just going to be G plus minus H. So it's like adding 2 games, but like you flip the players in one of them. Makes sense. So, does this work like subtraction? Do we have G minus G equals 0? And the answer is no, we don't exactly. And, well, the easiest way to see why this can't be true is that, like, 0 is a game where no one has any options. If you play a game like G minus G, then, well, generally you are going to have options, right? Like, you can move in G, and if G isn't 0, then that gives you at least 1 move, so it's not literally the 0 game. But fortunately, it is order equivalent to the 0 game. And this is actually one of those proofs that I would like to do. So yeah, let's actually do that pretty quick, right? Let's prove that G minus G is order equivalent to 0. So how do we do that? Let me just replace these 2 games by nothing. G and minus G. We're playing the sum of these 2 games. We want to prove that this order equivalent to 0. And well, what does order equivalent to 0 mean? We can just look at the chart. G order equivalent to 0 means that left wins G only as the second player. In fact, G being order equivalent to 0 is the same. I mean, this is the same thing as saying that the second player is always gonna be the one that wins. So let's prove that. How do we prove that the second player always wins this game? In fact, does anyone want to try to play this with me?
If I am player 2, I think so.
Alright, so I'm gonna start in. Let's say that I move G to, I don't know, some game H. We don't really know what the actual moves look like, but sure, we can kind of pretend.
I'll move negative G to negative H.
Ooh, nice. So what has happened? What just happened here? Well, a way to think about what just happened is kind of a symmetry argument. Basically I do a move here, you do another move here, And now we ended up in like basically the same situation as we started with, right? Except that instead of having a game like G minus G, now we have H minus H. And we could continue this, right? Like maybe I could move this to negative K, and then you could move this to K, and we could continue on, right? And the thing is, eventually we're going to have to get to something that's just 0 and 0. And, well, when this happens, then I'm going to be the next player, and I'm just going to lose, right? So, yeah, that's kind of how you can prove that G minus G is in fact order equivalent to 0. It's a bit shameful that we don't have like this strict equality, and again, this is like one of the reasons that like most authors like to just write this as equality. It means that like you get a nicer structure, you get like a commutative group instead of just a commutative monoid. But, well, you know, you can always work with like the quotient if you want, right? Like instead of talking about games, you can talk about games up to like this order equivalence relation, and then you do in fact get a group, and then everything is nice, right? So, yeah. There's also multiplication. I'm probably not going to explain a lot about this because this talk already went for a bit longer than I wanted it to. And, well, as you can see here, this is kind of like a mess. Multiplication is like one of those things that don't actually have a very good connection to combinatorial game theory. In fact, it's a pretty badly behaved operation. You do have like some things. You do have commutativity. You do have like G times 1 equals G. You have 0 times G equals 0. But associativity and distributivity are only true up to order equivalence. So it's kind of already not great. And then it's even worse because multiplication doesn't actually like respect this order equivalence relation. And what I mean by that is that like you can have games like G1 order equivalent to G2, but you have G1 times H not order equivalent to G2 times H. So yeah, this is like not a great thing, really. You can try to play it as a game. It's a really messy game. But I think it's better if I just skip this for the interest of time. Because I did at least want to get to like numeric games, right? Like that's kind of the title of the talk, serial numbers. So I think I'm gonna like at least get here and probably just gonna end the talk after that, or maybe I'll just like quickly gloss over everything else. So, yeah, numeric games. What's the idea here? Well, actually, let me check chat real quick just to see that no one has asked anything. G plus... Do you want to try chess plus checkers? Yeah, I think it would be kind of fun to just like try to play two games at once, as long as you ensure that one isn't just a negative of the other, because it's not going to be very fun. G plus 0 equals G. Yeah, that's actually just like a strict equality. Like it's not up to order equivalence. It just literally is true. And I mean, you can kind of see that because if you have like a game and then you're playing that but also the 0 game, then you can never actually do any moves in the 0 game. So it is basically just playing G. In Go terms, we might call those moves miai. I will have to disappoint you a bit because I don't actually know how to play Go. I'm really, really sorry. I know that I should probably learn this if I want to talk about CGT. But, well, I mean, that's a fun fact at the very least. Does this definition of multiplication work with the definition of the numbers? Like, is 2 times 3 equal to 6? It's order equivalent to 6. It's not literally equal to 6. The idea is that multiplication really only works in like certain restricted classes of games, and numbers are going to be one of those. Yeah. Maybe I'll explain a bit like where multiplication comes from after I explain what a numeric game is. So let me do that real quick. Numeric games. So a numeric game is going to be like some sort of subclass of all games. Like some games are numeric, some games are not numeric. And the way that we define what a numeric game is that, well, we kind of reason by analogy from other games that we've already seen. Like, for instance, 0, 1, -1, 1/2. 1/2, I think, is a particularly interesting example. Like I said, 1/2, we define it as 0 and 1. And, well, actually, I never actually explained why we call this 1/2, but it is literally just because 1/2 plus 1/2 is order equivalent to 1. So, like, the fractions do work in this sort of sense. And we also have, like, I don't know, 3/8 plus 3/8 is order equivalent to 3/4. Like, that's why the fractions get the names that they do. Because they do, in fact, like, when you add them up together, they do kind of behave like they should. And, well, that's also why you can call it like kind of a half move advantage, right? Like, if you're playing 2 copies of 1/2, then that kind of adds up to 1 move advantage. Again, it's kind of informal, but maybe it sort of makes sense. And, well, yeah, I say that a 1/2 is as a suggestive example because, well, in this case, we have 0 and we have 1. And we combine them together, we got a game that was like kind of smidged between these two. So that kind of suggests that something is going on, right? Like, maybe there's some sort of construction that, like, if you have 2 sets of games that, like, define some kind of interval, then maybe the game is just equal to something within that interval. And, well, yeah, numeric games essentially formalize that observation. And, well, let me just get to the definition. And a game is going to be numeric whenever... I'm going to have to make more space here. There really has to be an easier way to do this. So, a game is numeric. What happened? There we go. So we're going to say that a game, let's say, well, I'll just write like, I'll write it like this. GL, GR. So a game is numeric whenever, first of all of the games that it's made out of have to also be numeric, right? So everything in GL and everything in GR is also going to be numeric. And, well, that kind of means that this is a recursive definition, right? So we will have, so for instance, in the base case of the game 0, then both of these sets are empty, so this is a vacuously true condition, right? That's one of the conditions. It has to be made out of numeric games, but, like, obviously if we just set this, then every single game would be numeric, right? Like, this isn't interesting yet. The other condition is the interesting one. If we have anything in the left set, it has to be less than everything in the right set. That's the actual important condition here. And so we can look at some examples, right? So, for instance, 0, well, the left and right sets are empty, so all of this is vacuously true, right? Like, for everything in the empty set, well, it doesn't matter what the predicate is, it's always going to be true because there's nothing in the empty set. So 0 is numeric. That's kind of boring. What else do we have? We have, for instance, 1. 1 was equal to 0 in the empty set. 0 is numeric, so we already have this first condition. And 0 is less than everything in the empty set because there's nothing in the empty set, so yeah, that's numeric as well. On a similar token, -1, well, that's also numeric and also not very interesting. What about 1/2? 1/2 we were defining as 0, 1. Well, 0 and 1 are numeric. We already saw that. and 0 is less than 1. I mean, you can kind of believe that. Or actually, you don't have to believe me on this. We already saw that 1 was always won by left, whether it was the first or second player. So that does mean that 0 is less than 1. And so, 1/2 is a numeric game. Other examples, well, we already saw like 1/4 and 3/8 and all of these other fractions. They're also numeric. And in fact, this kind of ties to a question that someone made earlier in the talk that was what's going on with this game. 1/2, 1/4. This is a valid game, but it's not a numeric game, because even though 1/2 and 1/4 are numeric games, we don't have this inequality. This is just not true, so it's not going to be a numeric game. It's going to be some other kind of game. And, for other non-examples of numeric games, there's also Star, which also explains why we didn't have a better name for it, right? Star is the game 0, 0. Well, 0 is not less than 0, so it's not numeric, right? Let me see if anyone has written anything here. Oh, we're still talking about Go. Sorry, I really wish that I could comment on this, but I don't know how to play Go. I should really learn someday. So, 0, 1, 1/2, those are kind of examples of numeric games. Omega, that would also be an example of a numeric game. In fact, all of the natural numbers and all of the ordinals, all of those are numeric games. So, bunch of numeric games. What does this have to do with the serial numbers? Well, I'm gonna get here really quickly, and in fact, I think I can get here right now. Yeah, let's just get into it. What actually are the serial numbers? It's been almost 2 hours, and I still haven't even defined the title of my talk, so I'm just gonna do that right now. A serial number is an equivalence class of numeric games up to order equivalence. That's it. That's the definition. And well, to explain what I mean by this, well, we already saw earlier that we can have numeric games that are order equivalent but not literally equal, and we had the example of 0, 1, and 1 bar nothing. Both of these are order equivalent to the number 2, but they're not literally equal. So basically what you do in the serial numbers is you say, well, actually they are now equal. I don't know if I can really assume that people here are familiar with the idea of quotients, but basically the idea is that a quotient is just some other structure that you build where things that you want to be equal are now equal. And assuming that your notion of equal satisfies the properties that it's supposed to, it's reflexive, it's transitive, it's symmetric, then you can always build these kinds of quotients. And while the serial numbers are really just one example here. So you might say, for instance, that these two games, they're different as games, but they're equal in a quotient, or they're equal as serial numbers. That does make sense, right? Yeah, the thing is that it doesn't really matter what a quotient actually is. People often describe it as equivalence classes, but really it's just making the qualities work as you want them to. A quotient is really just that. And so the idea is that, well, actually, let me wait to see if you. I see that someone is typing. Yeah, it's kind of the same idea as fractions, in fact. 1/3 and 2/6, you can they're different pairs of natural numbers, but you can define fractions as a certain quotient of pairs of natural numbers, and in that quotient, 1/3 and 2/6 are exactly the same. And that's kind of the same that's going to be happening here with serial numbers. Like, you have different representations for any particular game. In fact, you might have you'll usually have like infinitely many representations for any particular game. But yeah, they all correspond to like one single serial number. Is there a reduced form of a serial number? Yes and no. There are reduced forms of finite games. For infinite games, this doesn't really hold, but there are other like canonical ways to like write down a single serial number. So, like, for instance, sine sequences. I kind of wanted to get to sine sequences, but I think I'm gonna have to do that in like a part 2. So let me now just wow you with this diagram right here. This is a small sampling, and I really do mean a very small sampling of the serial numbers. We can sort of see them. Well, we have a sort of tree structure. I don't think I'll get to explain what exactly this tree structure means, but it might at least make some intuitive sense. Like, for instance, the very simplest serial number we can make is just 0. Like, 0 is just 2 empty sets, so it's kind of like the first serial that we can build in some sense. Then -1, we build that one using 0 as the left set. No, sorry, as the right set. So yeah, -1 is like made out of 0 and nothing else, so we put it here like in the left of 0. We also have 1, which is also made out of 0 and nothing else, so we put it here to the right. Then in the next row we have like -2, which is made out of -1 and nothing else. We have -1/2, which, well, -1/2 is just this game, right? -1 and 0. So it's like made out of -1 and it's made out of 0, so it kind of gets a spot here in the middle. Again, I can't really explain like concisely what the branches mean at this very moment, but you can at least tell that like from left to right, this is just kind of like the standard ordering of like numbers, right? Like we have -3, then -2, then -1, then -1/2, then 0, then like everything is kind of in order from left to right. Top to bottom, that's a bit more difficult to explain, but yeah. What else do we have here? If we keep going through the left branch, then we'll eventually get to -omega, which I did mention a bit earlier that like omega was an example of a numeric game, and so that implies that it also corresponds to a serial number, right? We have -omega on this side. We have +omega if we just keep following the right branch. We have a bunch of other things here in the middle. For instance, if we kind of take this alternating path, 0, 1, 1/2, 3/4, 5/8, and we continue, we eventually end up on 2/3 of all things. That's pretty neat. If we take one right branch and then we just continue to go into the left, to the left, to the left, we eventually land at epsilon, which I don't like calling epsilon. It's just like one. It's just a reciprocal of omega, but you know, it's kind of it's an infinitesimal, so you can like write it down as an epsilon if you want. And you know, this tree continues down here. You have epsilon over 2, 2 times epsilon. We have here other different like fractions of epsilon. We can continue going down here, but the diagram doesn't, because again, it's a very small diagram. It has only a very small fraction of all of the serials. What else do we have? If we continue going through the right branch after omega, we have omega plus 1, omega plus 2, up to 2 times omega, and then 3 times omega, and then if we continue going, we end up at omega squared. Or what else do we have? If we get to omega and then take a left turn, we end up with omega minus 1, which if you know anything about the ordinals, this should strike you as really weird, but that's a serial number, that's no problem. We can continue going and end up at 1/2 of omega. Then we can continue going get to 1/4 of omega, and eventually getting to the square root of omega, which, again, kind of odd. Or we could have taken a right turn here and gotten to 3/4 of omega, and then you can kind of imagine how we get all of the other fractions of omega. We have omega plus epsilon here. So, just a whole lot of numbers. Yeah. And you have like all sorts of other very weird constructions. Like you can take like cube roots of omega, or you can take like omega to the omega, or you can continue to like uncountable ordinals, or you can continue to like their reciprocals. The serials are a very, very big structure. And well, yeah, that's again why I insist that this is just a very small collection of them. What else do we have here? Like, for instance, if I went to 3 and then took some branches selectively, going like to the right and a lot to the left and then a bit more to the right, I might end up with pi somewhere in here. Or really, if I keep taking my left and right turns selectively, I can land at any real number. So, yeah, the zeros at the very least contain all of the real numbers, they contain all of the ordinals, and they contain a lot of arithmetic that you can perform on them, which, I mean, really, I think that any structure that contains both the ordinals and the real numbers has to be a very weird structure. Let me see if there's any questions. 1/8 equals 1/8 plus epsilon? No. The serials are a field. I haven't really gotten to that yet, but basically it means that you can like add, subtract, multiply, divide, and it all kind of works out. And well, yeah, a consequence of that is that like 1/8 plus epsilon equals to 1/8. That would imply epsilon equals 0, and that's not gonna work. Anything that does not have a power of 2 as the denominator will need an infinite number of splits. Yeah, that's in fact one of the basic results. Like if you take this tree here and you look only at like the first finite number of branches, like this is like level 0, level 1, 2, 3, 4. If you only look at the finite levels, you will only find fractions that have a power of 2 as a denominator. And conversely, any fraction that has a power of 2 as a denominator is going to be found somewhere here at the like first finitely many layers. So yeah, again, I'm not gonna go over any proofs here, but that's something that you can in fact prove. And then like all of the other real numbers, the ones like 2/3 and pi and whatnot, those are going to be at like the layer, at the first infinite layer, or layer omega if you want, which is also going to contain things like epsilon and omega and negative omega. Let me see what else. Yeah, exactly. Like the non-dyadic, dyadic just means like denominator is a power of 2. All of them are gonna need like an infinite number of splits. So 2/3 equals 1/2 plus 1/8 plus 1/32. Yeah. Though I think a better way to think of it is that 2/3 is 1 minus 1/2 plus a fourth minus 1/8 plus 1/16 minus 1/32. That's kind of what's going on here. And, well, yeah, that's kind of just a geometric sum, so... And yeah, I kind of wish that I could explain what the branches actually mean. They're related to, like, this notion of what's known as the simplicity relation in serials. But, again, I think I am going to have to do a part 2. It's almost been 2 hours. That's kind of insane. So let me just, like, quickly go over things that you can do with the serial numbers. You can add them, and the way you add them is literally just like add them as games, right? Like the thing is, if you have two games G and H, I think I didn't mention this explicitly. I probably should have, but if you have two games G and H, well, actually, if you have games like G1 order equivalent to G2 and H1 order equivalent to H2, then you have G1 plus H1 is order equivalent to G2 plus H2. So basically, what that means is that order equivalent it basically means that to add two surreals, you can just like take any two representatives and add them together, and then whatever that gives you, that's going to correspond to like the serial number. Like in a more categorical way, you can say that addition lifts from the games to the surreals, right? And I said that this wasn't true for multiplication, but as it so happens, specifically for numeric games, this does actually work out. And the proof of this is genuinely the worst inductive proof in all of mathematics. I am not exaggerating one bit. I don't remember the actual, like, at some point I counted the number of cases that you had to do. I think I counted like 56. It's a terrible proof, but again, I'm not going over proof, so I don't have to explain that. But basically, it means that you can also multiply serials together. And, well, through another pretty complicated proof, then you can actually even construct like a sort of explicit inverse. And that proves that the serials are not just a ring, but in fact a field. You can add, subtract, multiply, and divide, and it all kind of works out. And in fact, it's even more impressive than that. Like, this is another thing that I'm just not going to have the time to explain and much less the time to prove. But the serials are not just a field, but actually what's known as closed field. And what real closed means is essentially that you can solve the same kinds of polynomials as you can in the real numbers. So, for instance, with the real numbers, you can like take square roots of any positive element. So like, if a is greater or equal to 0, and the polynomial x squared minus a has a root, which is given by, well, actually has two roots, which are given by like the positive and negative square roots of a. And if you have a polynomial of odd degree, so something like, I don't know, x cubed plus, I don't know, pi times x minus 7, then that can also be solved in the reals. And what real closed means is essentially that you can solve these two kinds of polynomials as well over the surreals. Like, you can always take square roots, and you can always solve polynomials of odd degree, which also means that you can take cube roots and fifth roots and everything else. And yeah, this is all pretty... I mean, I think the fact that you get all of this by just thinking about games is kind of impressive. But it means that like all of these games, like square root of omega or like the, I don't know, cubed root of epsilon, you can always do all that kind of stuff. It just kind of works out. Is epsilon equals to minus epsilon? No, that's not true. I probably should have mentioned that a bit. I should probably mention that explicitly. But the serials are going to be linearly. They are linearly ordered. Like I mentioned earlier, that like games had this weird sort of comparison where like they weren't only like reflexive and transitive. But if you talk about numeric games specifically, then it all kind of works out much better. Like, you have anti-symmetry because you're doing this quotient thing. And in fact, the serials are a total order, which means for any two serials x and y, you either have x is less or equal to y, or y is less or equal to x. So they're a total order. That's kind of neat. And well, yeah, the thing is, epsilon equals to minus epsilon. Well, you can't have these sorts of equalities. I mean, it's this... The serials form a field, and that basically means that algebra in them kind of works as you expect. And well, one of the... Using just basic, like, laws of algebra, we can kind of say, oh, if epsilon equals minus epsilon, then 2 epsilon equals 0, then epsilon equals 0. So yeah, if epsilon is not equal to 0, then this is not going to be true. Can someone... I remind of what a number is. See, I want to give a talk about numbers. That's like another topic that I'm like really interested in. But basically, no, the numbers are not a subset of the serial numbers. They're like two different kinds of structures. In fact, the numbers are a different sort of, like, we defined serial numbers from like a specific subclass of games which we call numeric. The numbers are what you get when you consider a different subclass of games which are called impartial. And basically an impartial game is one where like the left and the right players always have the exact same set of moves. So if you do that, then you get what are known as the numbers, and that's a different sort of structure, which is also like really, really, really cool, but it's not the serial numbers. Is negative epsilon less than epsilon? Yeah, epsilon is going to be positive. And yeah, epsilon is not going to be confused with 0 because they are total orders, so yeah, nothing is confusing about the serials. And I kind of... Sorry, I shouldn't say that. The serials are like... Yeah, you're never going to have X confused with Y because they're a total order. In fact, that's kind of what this means. So the serials are confusing, but they're not confused with each other. Yeah, you basically... minus epsilon is less than 0, which is less than epsilon. That's kind of what you actually have. I should probably mention that, like, the existence of, like, an infinitesimal is not actually, like, this huge sort of thing. Like, there are a lot of fields that have, like, infinitesimal or infinite elements. Like, if you've already worked with, like, rational functions, for instance, which rational functions are just, like, a polynomial divided by another, you can also, like, order them in such a way that, like, you get infinite elements, which would be, like, powers of your indeterminate x. Or you can also get, like, infinitesimals, like the rational function x to the minus 1. In some sort of way, this is already, like, an infinitesimal element, so the fact that serials have those is not, like, super surprising in itself. There are other structures that do have that. But yeah, they're like... I mean, I think there's a lot of other things that are interesting about the serials. Or, like, for instance, the hyperreals, that's another example of, like, a field which has, like, these sorts of infinitesimal elements. Which, I mean, again, there's another talk on this channel about the hyperreals, so I should probably plug that in as well. And, well, yeah, it's already been 2 hours, so I really do want to get this wrapped up. I think I am going to, in fact, have to do a part 2. But I might as well, like, at least talk about what other kinds of things you can do with the serials. I'm not going to go into detail into any of this, but, I mean, I don't know, it can be sort of a teaser. What can you do? You have infinitesimals, you have real numbers, you have infinite numbers, that we already kind of observed. And have here a few examples, right? Like omega, you can describe it as like the serial that arises from this game, right? 0, 1, 2, 3, all of the natural numbers as options for left and nothing for right. Or we have epsilon, which we can describe as the left player can only move to 0, but the right player can move to 1 or 1/2 or 1/4 or 1/8 or 1/16 to all of these like powers of 2. Or we can also have like 1 plus epsilon, so that would be the game where left can move to 1 and right can move to 2 or 3/3 or like 1.5 or 1.25 or 1.125. Basically all of the real numbers that are larger than 1. What else do we have? We have a way of like taking powers of omega, which is kind of interesting. I don't know why I say kind of. It's actually like super really cool. Yeah, I'm not gonna go into detail in this because but basically this is a function that like, it's a pretty interesting function. Basically, you can plug in any serial in here, and what it's going to do is basically going to like, well, I don't know if I can give a quick description, but I don't know, if you want clickbait, you can take omega to the power of pi. That's really cool. What else can you do with them? There's like these infinite series that you can make out of surreals, which is pretty cool. Yeah, I kind of wanted to like give a bit of a. It's kind of a shame that I don't get to talk about this for very long, but these are all pretty cool things that you can do with the surreals. There's a bunch of questions that we don't know about the surreals. We have an exponential map. You can have sines and cosines of surreal numbers. Wow, yeah, just a lot of stuff, and now I'm getting a bit sad that I don't get to mention it, so maybe I should just stop here. Yeah. I think that's gonna have to be it for right now.
I have to go anyway, so good timing.
Yeah. I will talk about all of this. If I do get to give another talk, then I'm going to really go more into depth into this. Like, what do the branches in the tree actually mean? How do you actually, like, what sorts of operations you can do with, like, these sorts of strings of surreals? What does, like, this sort of, like, power of omega actually look like, and what does it actually do? What happens with all of these infinitesimals and these infinite numbers? What can you do with them? A lot of that, but I think I'm just gonna save it for the next talk.
Okay, sounds good. See you later. I'm gonna cut the recording.